and Dan are acting also as co-hosts. So if you see somebody who needs to be admitted and I don't see them, please let them in. Welcome everyone to our Regace project's final conference, the Agrivoltaics in Greenhouses, talking about turning sunlight into energy in crops. We would like to welcome all of you. Thank you so much for coming. Thank you for your interest in this project and our results. My name is Raymond Slaughter. I'm part of the project management and coordination team. I'll be moderating today, and I will just do a little bit of introduction here and a little bit of housekeeping before I introduce our project coordinator for the introductory section. So housekeeping, as they say, as you heard, we are recording today's session. We will send you a link to the video afterwards, so you will have it if you want to look back at it again, or if you would like to share that with others. As always, on such a call like this, please mute your microphones and turn off your video when not speaking. We have, I think, close to 200 registrations for this call, so we never know how many people are going to show up, but let's see. That's a big group, so also helps with the bandwidth and the background noise if everybody's consistently muting and turning off the video. As far as questions and answers, please go ahead and feel free to type your questions into the chat at any time during the meeting. We won't stop after every presentation due to time limits. We won't stop for questions every time. But go ahead and type your questions in at any time. Maybe some of the presenters could answer questions through the chat. If you have more in-depth questions, you'd like to get in touch with us more in depth, please feel free to share some contact information, particularly if you're a farmer or have a greenhouse you're interested in implementing, definitely get in touch with us. We will have a question and discussion portion at the end, so we will try to give some time for discussion, but don't be shy about typing questions into the chat at any time. Now, the agenda, you've seen this as we sent out the invitations, and you saw this on the landing page. We will have a welcome from our project coordinator in a moment, and then we will start with the diversity of the 6 pilots that we've had across 5 different countries, and give you a little bit of an overview of the various pilot locations, and then we'll go into some more depth there on the Greek location particularly. Then we've got 2 main blocks about our experimental results and about the broader impacts of agrivoltaics and our project. In the first block, we'll talk about each type of technology individually. So how was the agrivoltaic performance, the PV performance? Then look into the CO2 methods and what was the impact of those. Of course, looking at the crop performance under the agrivoltaic systems and how that's performed during our pilots. Then a bit about the digital modeling and digital twins to collect all of our data and use that data in a useful manner. And then the second block is about broader impacts. So looking at the bigger picture, we've had a lot of contact with farmers and greenhouse owners, and we'll get some look into the farmers' perceptions, how they view the use of agrivoltaics, and then move into sort of the overall impact, looking particularly at sustainability aspects, socially, environmentally, and economically, and moving from there into some policy recommendations for agrivoltaics, fairly new field, and the policy landscape and regulatory landscape is still difficult and challenging. So look at some policy aspects there. And then moving in towards the business aspects and moving from the research to the market. We will be marketing and selling this technology in the future. So we'll have a look into that. And then, as I said before, we'll have a question and conclusion session at the end. And so, without further delay, I would like to introduce Ibrahim Yehia from the Al-Zawqawi Society, the Triangle Research and Development Center. He's the project coordinator of Regace. Ibrahim, would you like to say a few words? You're on mute.
Yeah.
Yeah, good.
Okay, thank you very much, Raymond. Good morning, everyone, or good evening. Ladies and gentlemen, dear partners, distinguished guests, colleagues, and friends. Indeed, it's a privilege to open the Regace Final Conference, a unique project that brings together energy, agriculture, innovation, and real-world implementation to demonstrate how agrivoltaic can contribute to more resilient and sustainable European food and energy systems. This conference takes place at a high significant moment. We are facing profound challenges: climate change, increasing pressure on land and water resources, energy uncertainty, and a growing need for solutions that successfully integrate food production, energy generation, and community resilience. Regace was born from this understanding that the solution of the future must be integrated, intelligent, and practical. Agrivoltaic, and in particular, its application within greenhouses, is no longer an experimental concept or an academic vision. It's a proven, data-driven solution based on research, pilot project, and real-world experience. Importantly, the investment in Regace is already delivering tangible value for agriculture itself, improving farmer productivity and resilience, reducing operational costs, and strengthening farmers' economic stability, while supporting the broader energy transition. In simple terms, less competition between agriculture and energy and more synergy. Before I begin, I would like to acknowledge two individuals whose support has been essential to the practical progress of this project. I sincerely thank Mrs. Irena Benido, our European project officer during the first phase of the project, for her dedicated guidance, and Mrs. Maria Laura Trifiletti, our current European project officer, for supporting the project through its final phase towards successful completion. On behalf of the Regace team, I would like deeply to thank Mr. Raymond Slaughter and Simon Van Dam for the significant contribution to the project's success, as well as my team at the RDC for their hard and dedicated work. This project wouldn't have been possible without a true collaboration between researchers, engineers, farmers, industry, and public bodies. I especially thank all our project partners for their commitment and collaboration spirit. Namely, I would like to thank Professor Cristina Cornaro and Professor Andrea Volterrani and their team from Tor Vergata University in Rome, Professor Anna Keutgen and Professor Norbert Keutgen from Boku University in Wien, Professor Nikos Katsoulas and Professor Cristina Babanioa from Tisar University in Volos, Professor Uwe Schmidt and Dr. Thorsten Roksch from Humboldt University in Berlin, Dr. Liron Amdur from Tel Aviv University, Max Liebrich from Biofarm Watzkendorf in Germany, Ezgi Ercan from Timelix Company in Brussels, Dan Gerstenfeld, Boaz Babai from Interteam Israel. And special thanks goes to Dr. Marco Di Stefano for the first pilot in his farm and for his great hospitality and tasty cheese. Thanks also goes to Dr. Esther Majadli for her input in the first phase of the project. Indeed, it was a great pleasure working with you all. I would like also to express our gratitude to the European Union and SINEA for their support and trust in both the project and its vision. Ladies and gentlemen, today is not only the conclusion of Regace, it is the starting point for the next phase, translating results into policy, standards, and large-scale deployment. I wish us all a productive and inspiring conference. Thank you very much.
Very good. Thank you very much, Ibrahim. Thank you for all the kind words and the welcome. So now we will begin with our first presentation, Diversity of 6 Pilots in 5 Countries, from Cristina Papiaanu and Nicolas Katsoulas. If you would like to go ahead and share your screen, you can begin. Nikos and
Yes, just
Cristina.
please.
There you are.
Sharing, yes. Is it okay? Can you see my screen?
Yes, it's there. Thanks.
Okay. Okay. So thank you very much for inviting us to give this presentation in this final conference of the Regace project. And of course, I would like to thank the coordinator for coordinating this work that now comes to the end. So, our presentation is related to the pilots in the 5 countries. We do have 6 pilots that were tested during the life size cycle of the project. And of course, I believe that we'll continue working beyond the project, as at least is our scope at the University of Thessaly, our aim to continue working with photovoltaics and produce more results after the end of the project. So we will have a presentation of the pilots in the different countries, and we can see that in this map that we have 6 pilots starting from Israel in Kafr Kara, then going north in Greece, in Volos, it's in the center of Greece, in Rome, in Italy, in Vienna, in Austria, and then going farther north from Berlin to Waskendorf. So we do have 6 pilots that are spread around in Europe, from south to the north, so that we have different climate conditions, hot or dry, and humid and cloud in the north, and more lower temperatures in the northern regions. So we can have a quick look from to each of the pilots. All the pilots have the same photovoltaic panels. And this is the idea of testing the same panels around the different locations. So we have the panels installed in a research facility in Al Zarqawi Society at Israel, in 4 arched greenhouses of the same size, used of course for the different treatments as control in some cases, that is without installing photovoltaics, just for the purposes of control, of benchmarking the results that will be provided by the greenhouse that have photovoltaics. So we had here 4 different compartments with a total installed area of installed capacity of 12.6 kilowatts. In the greenhouse, there were tested different crops: cucumber, lettuce, bell pepper, during different periods of the year. And the greenhouse was enriched also with CO2 provided by bottles that were connected to the greenhouse environment. There were many sensors connected in the greenhouse in order to have a distribution of the microclimate and of the radiation inside and outside the greenhouse, of course, and the climate control of the greenhouse was also present. Basic parameters that were measured were temperature, relative humidity, CO2 concentration, photosynthetically active radiation, global radiation, diffuse radiation in some cases in the greenhouse. And the greenhouses, of course, were used during the life cycle of the project in order to test the different treatments that were produced in the project. Going to the case of Greece, there were again 4 compartments for greenhouses where the photovoltaics were installed. Here we had the Gothic type greenhouse of higher gutter height than in the previous case, with a total power installed in the two compartments of 14.4 kilowatts with 96 panels in each compartment, in each unit. The same method was used for the application of CO2, for the enrichment of the greenhouse with CO2. And here the crops were tested were cucumber and lettuce. Following again the same paradigm, the same protocol for the sensors, and this is the same for all locations, so that we have in all cases measurements of temperature, humidity, CO2 concentration, and of radiation, of course, inside, below and above the panels and outside the greenhouse. So just to make clear that in all locations, the same measurements were taken, and almost there was an effort to unify also the measurements that were related to the crop characteristics. So going now to Italy, in this case, there were two compartments that were tested, the control and the greenhouse with photovoltaics, with 5.12 kilowatt of total power installed capacity of the photovoltaics. The photovoltaics were installed in Fattoria Solidale del Circeo and the University of Rome, Tor Vergata, that were both working in this pilot site in order to produce the results that will be shown later on in the different presentations. In this case, zucchini, cucumber, and tomato were tested as crops. So as far as we see up to now, we do have in all locations at least cucumber up to now that will be tested and compared between the different treatments and locations. Going now northward to Austria, in Vienna, in Boku, the University of Natural Resources and Life Sciences, we do have again here a greenhouse, three compartments with the photovoltaics tested in two compartments and one used as control, with a lower power capacity installed here, 1.32 kilowatts. And again, with basil, lettuce, cucumber, bell pepper, and radish tested as crops in the different treatments and experiments carried out during the project. In this case, CO2 was provided by CO2 bags that released the CO2 inside the greenhouse in a semi, let's say, automatic method. While in the previous locations, the control of CO2 was automatically controlled by the greenhouse climate computer. In Berlin, one of the two locations in Germany, the photovoltaics were installed in a research facility of Humboldt University of Berlin with a greenhouse, one greenhouse compartment tested, splitted in different parts in order to test the effect of shading in the different locations inside the same greenhouse. CO2 was applied also in this case, and lettuce and tomato were tested in these locations. Of course, all the measurements and automations were used, again, as in the previous locations. And in the last location, in Waskendorf, in Germany, the northern one, the photovoltaics were installed in a commercial farm, in this case, of Biogartnery Waskendorf, in a greenhouse, of course, commercial in this case, with high height of gutter and rides. In a part of the greenhouse, of course, the photovoltaics were installed, and the crops tested here were again tomato, cucumber, and lettuce, with the same almost protocol for measurements related to the climate and the crop, of course. So this is a first view of the general idea, let's say, of the locations tested and of the greenhouses used. And we will see some more details in relation to the protocol used in a specific location, in this case in Greece. This was the greenhouse that was used for the experiments. You can see a greenhouse with 6 compartments. It's a Gothic type greenhouse with a height of 5 meters in the gutter and a length of 25 meters per compartment and 9.6 meters width for each compartment. So in this greenhouse, the outside compartments, that is, let's say, compartment 1 and compartment 6, were not used in the experiments, were used as border compartments in order to avoid having different effects of the environment. And the other 4 compartments were used for the experiments in the greenhouse with the photovoltaics. Here you can see the rest of the greenhouses that the University of Thessaly, of course, has in its facilities. You can see, I suppose, here the tracking of the photovoltaics tested in our facility. And in this case, we used 2 compartments with photovoltaics, and the other 2 were used as control. Monocrystalline bifacial transparent photovoltaic modules were used in all locations, as already said. And you saw, of course, the responsive tracking system working in the greenhouse. Responsive means that we controlled the tracking of the photovoltaics in relation to the objectives of each experiment, either having full tracking, that is following the sun, or having different, let's say, protocols for the tracking, depending on the treatment that we wanted to have in each of the experiments tested. 96 modules per compartment were used, and each compartment had an area of 240 square meters. And we had about 36% roof coverage in this case in the greenhouse. The photovoltaics were installed about 0.5 meters above the gutter. The gutter was at a height of 5 meters, so the photovoltaics were installed at about 5.5 meters from the ground, and were installed in the already, let's say, structure or available structure of the greenhouse, with only a few additional modifications in relation to the structure that we had already in the greenhouse. That is, we built the modules after having already built the greenhouse. The installed power was 7.2 kilowatt per compartment of 240 square meters. So in total, 2 greenhouses, the total was 14.4 kilowatt of installed power. And we had tracking initiation depending on solar radiation, on daily light integral or sun position. So we had different experiments starting from September of 2024 and finishing in October 2025. And here you can see the different compartments, 2 with photovoltaics, 2 without photovoltaics. And since we wanted to test also the CO2 enrichment, in the 2 compartments with the photovoltaics, one of the compartments was used to enrich the environment with CO2. So comparing the 2 compartments with photovoltaics, we could see the effect of CO2 in our experiments. And of course, we wanted to see the effect of photovoltaics compared to a control or a CO2 enriched greenhouse. to see the effect again of CO2 or of the photovoltaics. This was the experimental plan, and here you can see also the measurements that were taken. I think I have not to give more details about this. You can see here the tracking, how was performed inside the greenhouse from the top or below. And if you can see this image here, you will see that while now, let's say, we can clearly see the panels, in a few seconds, you will see that the panels will almost disappear from our view because they turn in a way that can leave the sun coming in the greenhouse if needed. So they can have full shading or zero shading, let's say, in the greenhouse, depending on the position of the sun. And this is very important in order to control the shading that we need inside the greenhouse. Just a quick look from some indicative results. I will not give many details. No effect was the main result, no significant effect, at least in the different periods of the photovoltaics on yield. And light, the leaf area index and the water use efficiency were improved under photovoltaics, especially under tracking and CO2 enrichment. So the message is that we can use the photovoltaics, track the photovoltaics in a way that will not have any effect on the crop. In some cases may improve the water use efficiency and the light use efficiency in the greenhouse, of course, and have, of course, the benefit of the electricity produced in our greenhouse. Here you can see some indication of the light that we had in the greenhouse. In this first graph, you can see the outside solar radiation. With the orange line here, you can see the radiation inside the greenhouse without photovoltaics, and with the green light line here, you can see the radiation in a greenhouse with photovoltaics. So we do have some shading when full tracking is followed. And this example is here for a sunny day and for a day with clouds. And in the case of the day with clouds, of course, the differences between the treatments are lower. And another case that we tested is the activation of screens, thermal screens as shading screens inside the greenhouse. And in this case, of course, the effect of photovoltaics was again minimized. However, we can say that when we used the screen to shade the greenhouse, the screen was located below the photovoltaics, of course, in order to have a proper use of photovoltaics and again the screen for further shading. The screen increased the performance of photovoltaics about 12 to 15%. That is, the reflected light increased the electricity production in the greenhouse. However, we think that we can use only the photovoltaics for shading without further use of the screens, and we can then shade exactly the amount of light we need to leave the amount of light we need in the greenhouse, because the tracking can leave us this possibility. Some indicative also lines showing the daily evolution of the CO2 inside the greenhouses, and we can see here that when we enrich the greenhouse with CO2, we had, of course, higher concentration, and this affected, of course, our crop during the experiments, positively affected our crop. Just an indication of the transmission. In the control greenhouse, we had 71% transmission with clear sky, while in the greenhouse with photovoltaics, we had with full tracking transmission of 57%. Of course, we had a reduction in the transmission because we had full tracking of the photovoltaics, full sun tracking. And again, some differences in the transmission during cloud conditions. And here we can see the electricity production, the power output of the photovoltaics, depending on in relation also to the outside solar radiation. That we can see that the photovoltaics follow, of course, the curve of light, the radiation outside that we have in the greenhouse. And here, to go to the conclusions soon, we can see the electricity produced, the electrical powder production during the period of 2025 from March to October. And we can say that during this period, we had about 6,300 kilowatt hours produced in these 7 months. That is about 2.1 kilowatt hours per day per kilowatt of installed power. Some also results in relation to the CO2 emissions. We can see that the photovoltaics reduced the CO2 emissions per kilogram of production to about half of a conventional greenhouse. This is also an important finding from the pilot tested here in Greece. So going to the conclusions, no systematic significant effect on crop yield from the photovoltaics. That is something very promising, at least for this location. So it means that in locations like Greece or Italy or Israel, we do not expect a significant effect of photovoltaics as were installed in our case in about 30 to 35% coverage of the roof, no effect on yield. And positive results is that with this application, photovoltaics covered the electricity production, providing a surplus of 100%. That is, even with a 15% covering of our greenhouse roof, we could cover the electricity needs of the greenhouse, excluding, of course, the needs for heating. We mean the electricity needs of the rest of the greenhouse. Photovoltaics led to CO2 emissions reduction, and based on the data that we collected and the method of connecting the photovoltaics to the grid, we estimated that we have a payback period for the system of 3 years with net metering, as is the case of our greenhouse in Greece. It's connected to the grid with the system of net metering. That is, we sell and buy the electricity in the same value, in the same price, while with net billing, that is buying electricity from the grid almost double in the double price that than the one that we sell, will need about 6 years. And PV's photovoltaics tracking can be further improved, of course, in the system with additional work and modeling. That is something that we will follow doing during the next period. This is, I hope that I did not took much time. This is the first presentation of the pilots. And with this slide, I would like to thank you for your attention. And of course, thank to my colleague, Cristina Papaioannou, that coordinated the project for the Greek side, from the University of Thessaly. And of course, I have to not to miss to thank all the partners and of course the colleagues from the University of Thessaly that contributed in this work. Thank you very much.
Good. Thank you, Nikos. Thank you very much for your presentation. Remember, everyone, if you have questions for Nikos, feel free to write them in the chat, or if you need to get in touch personally, feel free to share some contact information. Our next presentation will go deeper into the agrivoltaic performance from our coordinator, Ibrahim Yehia. Ibrahim, if you'd like to go ahead and share your slides and unmute your microphone,
Yeah,
and you can.
immediately we are trying to manage it.
All right. We can see your slide coming up.
Okay,
Feel free to turn on your camera. There we go. Thank
can see?
you. Yes.
Fantastic. Okay. Thank you, Raymond, and hello again. In the next minute, I will present the agrivoltaic performance results of the Regace, focusing in greenhouse integrated system validated across different climates. The motivation behind Regace was simple yet ambitious to transform agricultural spaces into active contributors to the energy transition without sacrificing land, productivity, or landscape. From the outset, our goal was to move beyond theory and to demonstrate in real greenhouse and real climatic conditions that agrivoltaic can create tangible value while preserving the primary agricultural function. Regace introduced a systematic solution, one that saves land, reduces the need for additional energy infrastructure, minimize visual and environmental impact and enable uninterrupted agricultural activity. I will share what this collaboration has achieved in these 15 minutes. Okay, sorry. Yes, that's in big picture. Regace was designed to address global challenges in line with the SDGs and the EU Green Deal regarding climate change, energy security, food security, and decentralized system. Unlike many other projects, we focus on really greenhouse operation. So Regace offer part of this solution in order to ensure the food security and energy security, low environmental footprint, and dual use of land. We can look what's going on, what's happening now in the field for agrivoltaics model. Many existing agrivoltaic models suffer from high infrastructure requirements, limited flexibility, and indeed negative impact on agricultural operation, as you can see here in the pictures. Most are static design, difficult to adapt across crops, regions, and landscapes. Meanwhile, the Regace integrated agrivoltaics directly in existing greenhouse enables simultaneous energy production and agriculture without additional land or major infrastructure. The system is dynamic, scalable, and farmer-friendly. Here, the picture, you can see how the system is so easy to install, simple way, lightweight, and don't require any additional infrastructure. It's really react to environmental condition rather than remaining static. We tested this system in 6 pilot greenhouses in 5 different countries, as Nikos mentioned before. This allows us to test the system concept, the same concept in different climate within the context of real greenhouse operation. Allow us to compare performance in a consistent and meaningful way. Regace used custom designed bifacial models. We have tested here 4 different type of model based in greenhouse requirements. We can adapt then the light requirements. Those are not off-shelf models. We designed different model structure with different light transparency, both based on location need, crop need, etc. So the key question we addressed is whether agrivoltaic system inside the greenhouses can deliver a stable, scalable, and predictable electrical performance across different climate zones. We used continuous electrical monitoring and the same KPIs across all sites. Importantly, comparisons were made by climate category and not by country. The key indicators included energy yield, performance ratio, ground coverage ratio, seasonal adaptability, and operation stability. We analyzed daily, weekly, and monthly energy yield across all sites, comparing inside versus outside the greenhouse performance, tracking versus fixed configuration, and beyond that, we evaluated thermal behavior and radiation distribution, including panel temperature, greenhouse temperature, and diffuse light effects. Validation was conducted at both the module and system level, including front and rear side functionality test and bifaciality assessment. Module degradation was evaluated using thermographical inspection, as you can see here in the picture. In addition, a performance comparison between bifacial and monofacial modules was carried out, demonstrating superior performance of the bifacial modules. Here we present the performance testing results from the Kvarkari site, showing how electrical output, temperature, and light behave together during real greenhouse operation. The schematic above here illustrates the panel layout. Three types of panel were monitored. You can see the blue line and the green color and the orange color. The three types of panels were monitored. The blue panel measure electrical performance at the overall system level, while the green and orange panels measure performance at individual panels level for tracking and fixed configuration. This step allows us direct comparison between panels installed inside and outside the greenhouse, as well as evaluation of both the full system and its individual components. To assess how the system affects conditions inside the greenhouse, multiple sensors, as Nikos mentioned, were installed at different height levels and monitor temperature and microclimate change. The AgriBV system website serves as a centralized platform for continuous collection of climate and power generation data. It enables real-time monitoring, performance analysis, and long-term assessment of the system before and under varying environmental conditions. Collected climate data includes light, intensity, greenhouse temperature, humidity, and CO2 level at different heights. All parameters have been continuously recorded every 5 minutes over the past 2 years across all Regace sites, enabling robust long-term analysis. The figure shows how the system reacts in different light distribution on a sunny day and compared with a rainy day. The tracking panel helps spread sunlight more evenly inside the greenhouse by constant changing their position during the day. This prevents strong light spots and deep shade, creating more uniform light conditions in the crops. In the bottom graph here downstairs, the green represents the position of the sun, orange shows the position of the panels, and the blue one is the difference between the sun position and the module angle. So on sunny days is a plenty of light, so the panel closely follow the sun and going or turn to full tracking mode, and in rainy or cloudy days when less light reach the plants, the panel moves away from the sun position to let more natural light pass through to the crops. In this, here we can see the light distribution within the greenhouse under sunny and rainy conditions when as the shading net is used. Other effect, as Nikos mentioned before, effect of shading net is that they reflect light to the rear side of the panels, resulting increasing of the power output of the system. The lower graph compare the power output production in both rainy and sunny days. The panel temperature within the greenhouse were only approximately between 5 to 7 degrees higher than the outside, which doesn't affect panel performance even in hot summer times. The graph, the right here, shows heat distribution inside the greenhouse when PV panels are installed. The warmest air stays in the top of the greenhouse above the panel, while the air closer to plants is cooler. This helps protect crops from heat stress. This graph presents the energy output of the PV modules installed at different locations. A reduction in power output is observed for modules inside the greenhouse, mainly as a result of shading from the greenhouse structure elements, with additional contribution from the light attenuation through the greenhouse plastic cover. It is important to note that the amount of light entering the greenhouse from outside is strongly affected by shading from greenhouse structure itself. We suggested using spectral selective greenhouse cover material that can improve both the PV system and the crop performance by optimizing wavelength transmission. In addition, we addressed this limitation. We have already designed a new PV cells that significantly reduce structural shading and improve system performance. Here, a general view demonstrates the stable, consistent yearly power generation, reflecting natural production profile aligned with local irradiance conditions. The annual yield follows expected seasonal pattern with no abnormal deviation, indicating healthy system behavior and reliable operation. As I mentioned earlier, we had pilot greenhouses in six locations. These can be divided in 3 climate zones: high and medium and low insolation, enabling true and real multi-climate validation. The monthly specific yield and performance ratio at 3 different climate sites show consistent and comparable trends, indicating stable electrical system behavior under different climate conditions. While specific yield varies seasonally in response to the local irradiance, the performance ratio remains relatively stable at all locations, reflecting reliable system efficiency. Overall, the results confirm robust PV system performance across all sites, despite the differences in the climate. And here we show the specific yield and performance ratio across all sites. The specific yield describes how much electricity the system produces per unit of installed capacity, and mainly depends on how much sunlight is available at each location. The performance ratio shows how efficiently the system converts sunlight into electricity and remains largely consistent regardless the location, reflecting overall system quality. The results show that the system performs similarly across all sites, indicating stable and reliable operation. The conclusion of our research indicate that agrivoltaic system can be successfully integrated within existing greenhouse. The electrical performance is stable across climates. Crop relevant light availability is governed by integrated system behavior, and response operation significantly improve the system balance. It is important to note that the Regace system requires minimal involvement from the farmer and does not affect agricultural activity. Regace demonstrate that agrivoltaic greenhouses are no longer experimental concept, but accessible, reliable, and deployable system. Thank you for your attention.
Good. Thank you very much, Ibrahim, for all of your inputs there. Again, if you have questions for Ibrahim, feel free to put them into the chat. But we will continue moving forward. The next presentation will be about the CO2 methods that have been used and the impacts. And that'll be from Jens Neumann from the Humboldt University of Berlin. Jens, would you like to share? We see your slides coming. And
Yeah.
there we see you as well. Good. Thank you.
Okay, can you see everything?
You're still not in presentation. There's the presentation mode. Yes, go ahead.
Okay,
Thanks.
wonderful, wonderful. Thank you everyone for joining. My name is Jens Neumann. I'm a research assistant here at Humboldt University. And I'd like to give you some of the insights of the implementation of these different CO2 systems that we worked with and some of the results that we gathered here. First, some background about CO2 and CO2 enrichments. So, of course, if we build PV modules in our greenhouses, we have a reduction of light. This is also associated with a reduction of yield. And the main idea was to compensate this light loss with a higher CO2 concentration in our greenhouses, hence the CO2 enrichments. Because in general, CO2 enrichment in greenhouses is associated with a higher biomass production and also is associated with a higher yield and therefore crop production. Yeah, the main idea was to compensate the light loss with the CO2, and we had different systems that we worked with. These CO2 enrichment systems were location specified. So we had different greenhouse systems that had different technical approaches on how we can produce or can actually install these CO2 enrichment systems. One of the most used systems that we had in our project, I show this on the map on the next slide, is technical CO2 via bottles. At Bukovine, we used CO2 bags. Later, we used the respiration of mushrooms that produce CO2 to enrich some of the greenhouse cabins. And there were also at the nursery in Watzkendorf different organic materials used, and also in Italy to use the natural CO2 from microorganisms when they work with green waste. To go over the map, so we see different systems in place in Israel and in our location at Humboldt University of Berlin. We used CO2 bottles, the same thing for Greece. And in Italy and in Watzkendorf, which is the most northern partner in our project, we used green waste. And in Bukovine, Vienna, we used mushroom and also CO2 bags as a system of CO2 enrichment. You can see the system from our greenhouse that we used on the top. This is our CO2 bottles. This is liquefied CO2 that is then connected to our greenhouse. There's a system that is connected with the climate control of the greenhouse so that we can control the CO2 level to the desired level that we want to have in the greenhouse. This was around 800 ppm as like the actual level that we want to have in the greenhouse. And we also used photo boxes, which is a form of a climate chamber, where we also did different experiments and also used CO2 enrichment in these to make really precise experiments with precise CO2 levels. But I get to this in a later slide. On the lower picture, you can see one of the green waste pictures of Biogärtnerei Watzkendorf. It's an organic farm, and they used natural green waste or organic matter as a CO2 source, and also show you some of the results from there. because we did also some measurements there to see how much CO2 is actually going to be released of like the result of microorganisms. To show you the photo boxes or phytotrons, as we call them, on the left side, you can see the actual chamber itself. We have three chambers of the same type. We have around 1 square meter of ground area. We have active heating and cooling, so we can adjust the temperature. We have new LED lights so that we can adjust the light setting and intensity just to the setting that we need them for our experiments. We have a precise regulation of the humidity, an accurate adjustment of CO2 levels, which was really critical for our experiments there. And of course, we have in this case also like irrigation systems and also software to control everything to get data loggers and all that kind of stuff. I get to the results in a few slides. The other big greenhouse that we have is also really high-tech greenhouse because we also have a really unusual heat exchanger system. This was also quite crucial for our experiments here. In the ZNEC greenhouse, this was actually built from another project, but we still use them for experimentation. The greenhouse itself is connected to a heat exchanger system so that we can actually cool down the greenhouse during hot summer month or when we have like high temperatures during daytime. We have different thin pipes installed, and these actually are filled with water that then collect the solar radiation in the greenhouse, and we can use this to store it in water storages, to use the heat via heat exchanger to then heat the greenhouse in the nighttime when the temperatures are usually lower. And we can also use the system to cool down and get some of the heat out of the greenhouse, and therefore also don't need to open the actual vents so often so that we can actually save on the technical CO2 that we used in the experiments. Then we go to the actual setup from our PV panels. As Nikos already mentioned, we were basically testing different shading conditions in our greenhouse. As you can see on the left side, we had a gradient shade from high to low. This was realized by putting different amounts of panels in the greenhouse itself. We have two control areas where we don't have any PV panels, and these have different shading coverings from roughly 21% or 22% shading to roughly 10.8% shading. This is another view of them. As you can see here on the right side, we have some tomato plants that we used for one of the experiments. On the left side, you can also see that for our greenhouse, the panels were specially adapted. These are like narrower than on the other locations. This is because we have different shading and different shading screens in our greenhouse already installed. And with the sun tracking, we had to design them a bit narrower so that we had like a location-specific adaptation of the system itself. Here you can see the implementation in Biogärtnerei Watzkendorf. As you can see here, they use the bigger panels on their cucumber greenhouse, and it's a large Venlo greenhouse. They are organic farms, so they only cultivate in soil and are not allowed to use mineral fertilizer. And this is why they have to use green waste or organic matter as a alternative CO2 source. And we also did some experimenting there to see how the impact of CO2 actually is. To get some of the results, so this is from an experiment that we did in our fighter boxes with Raphanos, which was Regace. As you can see on the left side, we have three different settings. Settings A was a CO2 level of 400 ppm with a light intensity of roughly 160 micromoles. And setting B was a higher CO2 concentration, about 800 ppm with the same light intensity. And chamber C was a higher CO2 level, but a decreased light intensity. This experiment was done to simulate the amount of shading that we would have on in a greenhouse itself on the plants. And the idea was like, can we actually compensate the light loss with a higher CO2 concentration? And as you can see here from Regace, this is the fresh weight of the bulbs and also the dry weight of the bulbs. And you can see here that these are all significantly different from each other. So the higher CO2 level and the full amount of light intensity produced like the highest fresh weight and the highest dry weight of all of these different groups. B was producing the second highest fresh weight and dry weight of all these groups, and the control one, the C1, was actually the A1, sorry. The A1 was the lowest one with with only 400 ppm CO2. So you can actually see from these results, this is of course only applies for Regace. This could be different from to other species, but for this test, you can see, or for this experiment, the results suggest that you can, of course, see that with a CO2 enrichment, you can compensate for a certain amount of light loss, which was here set at around like 15% light loss. In our big greenhouse, in the ZNEC greenhouse, we did different trials, as already mentioned before. We did different trials with the letters, where we had no impact of the PV panels in terms of fresh weight. We also did some trials with tomatoes that are more or less the same as you can see here for cucumbers in terms of the overall results. But we could see here these different groups like the control light, medium, and heavy shade, and the control group 2 are referring to the slide that I showed before with the different shading gradient. For the cucumbers and also for the tomatoes, we didn't see any difference in the biomass per plant between these different groups. The same with the shade gradient with the panels. We see a similar gradient in decrease of numbers of fruits per plant, and the same with the total fruit fresh weight per plant. So the control areas had the highest yield, and then continuing with the shading from light to heavy, the light shading areas, light and medium, had a similar but significantly less numbers of fruit per plant, and also less total fruit fresh weight per plant. And the area with the highest shading had also the lowest number of fruits per plant and the lowest number of total fruit fresh weight per plant. This was the same with the tomato trial that we did before that. So a certain amount of shading would decrease, or as the data here suggests, that a certain amount of shading would indeed increase the amount of yield that you would get from a given crop that you would grow. But it also shows that a light shading wouldn't make such an impact, but this actually depends on the crops you're growing and the amount of shading that you would actually get from the PV panels. With the organic matter, we did some measurements regarding the CO2 release from microorganic organisms. On the left side, you can see the CO2 concentration that was measured in the greenhouse itself at 2 different points. And as you can see, when they freshly brought in new organic matter, the CO2 rised up pretty quickly and fast within the first few days to really high levels. But then over the course of the next few months, it actually decreased quite rapidly. This actually suggests that some of the microorganisms are quite quickly developing and dividing itself and produce a lot of like CO2, but then most of the resources are kind of like used up, and then the CO2 amount that is released kind of like decreases quite rapidly. On the right side, you can see the same. We did we took some of the samples from the organic matter and put them into one of our laboratories, and then measured quite exactly and precise how much CO2 would actually be released from a given certain sample. And as you can see here, how the CO2 increased over a certain time, but then kind of like flattened out. And then the amount of CO2 wasn't really like adding up. So it's similar to the result on the left side. You see a quite fast release of CO2 in the early days when you apply the organic matter, but then after a certain amount of time, there is not much CO2 released again. So this would either suggest that you had to bring in organic matter multiple times during your cultivation period, or that you use this to boost the early plant growth, and then work with that. That would be another idea. Okay. The conclusions so far, yes, so increasing or CO2 enrichment itself can lead to higher yields. We've seen that, and it's in literature. It's a quite common agreement of most researchers. If the crops have lower light requirements, such as salad or cucumbers, you can actually use these PV panels with less worrying. If you have crops that probably have high light requirements, it's probably difficult to maintain yields at the same level. And the application of organic matter can release a significant amount of CO2, but there has to be some more further research on how long it actually can be released and what methods you can implement to increase the CO2 release over a certain period of time, so that you get like same levels of CO2 and not like a high spike of CO2 and then less CO2 over the rest course of the period. Okay, then thank you so much. Thank you for joining us, and I would give back to Raymond.
Thank you, Jens. Very good. There are at least a couple of questions for you in the chat, Jens. So if you'd like to jump in there and try to answer those through the chat, but we'll go ahead and move on with the next presentation. We're going to be talking about the crop performance under the agrivoltaic systems, and that's going to be from Norbert Keutgen. He's from the University of Natural Resources and Life Sciences, or Boku University in Vienna. Norbert?
Yes, I hope you can still see me.
Yes, there
and
you
hear
are.
me. The second slide you see as well.
Yes, background
So
slide.
everything is working.
Working well, thanks.
Thank you very much for the introduction. So I'm going to introduce to you some basic aspects of plant growth related to photovoltaic systems. And just look at the image here, and you can see a quite important aspect of PV modules. They are shading the plants. That can have a negative impact because light is necessary to run photosynthesis, and photosynthesis produces the carbohydrates important for growth. And the second but positive aspect is that shading results in cooling. However, this is not valid if you are constructing your PV within a greenhouse, because that means you are running into a greenhouse effect. The temperature is still accumulating in the greenhouse. In this aspect, it is quite interesting to have a look at the construction site in Israel, as you can see here, especially on the left image. The cover of the polytunnel was removed, and that means you can have a shading effect by the solar panels, and that means also a cooling effect. And it is well known from literature that this can have a quite positive effect on growth. On the other hand, referring to the presentation we had before, it is of course not making any sense to add additional CO2 into such an open system, because the CO2 will be released into the atmosphere almost immediately. When we did our experiments, you have seen the different locations from from Israel to northern Germany. The question was, should we use one cultivar for each locality, which enhances, of course, the compatibility of our results, or should we focus on the local cultures? And that was what we finally did, because this is increasing the practical relevance of the results. And that is possibly a very important aspect you may have to keep in mind when dealing with the results of that study, that we worked out quite important differences among the localities. Yet I'm going to give you only a short overview about the effect of light intensity of additional CO2 on some few examples, because the general results from all localities will be presented to you later. Here I would like to focus onto the so-called daily light integral, DLE, which we can roughly calculate from the mean light intensity to which the plants have been exposed. The daily light integral is what is recommended in literature, what the plants need for an adequate growth during the day. So here in this slide, you see pepper fruits. We have California, Wanda, and Bendigo, circle and square. These are bell pepper varieties. And we have a cayenne pepper, a variety indicated here by the triangle. In general, pepper is regarded as a light demanding crop. So the daily light integral should be between 20 and 30 mole per square meter per day. And you can see here on the table on the right side, we achieved in the best case some 16 mole, which is distinctly below what is recommended. But you also see quite distinctly that yield is heavily affected by the light that is available to the plants. Now, when it comes to the effect of additional CO2, I'd like to show you here a result from Brazil. We have two curves, one in blue, one in red. Blue is the control and red is the aspect of elevated CO2. The recommended daily light integral for Brazil is between 12 and 25 mole per square meter per day. And you can see here with the highest light intensity of the control, we are already reaching what is recommended for Brazil. The CO2 concentration under normal conditions was about 430, under enriched conditions about 580 ppm, so a significant increase was achieved. And what was somewhat surprising, at a low light intensity, 100 micromole, there was almost no difference between the control and the elevated CO2 aspect, while in the case of 150 micromole light intensity, we had already a higher yield than was achieved with a light intensity under control conditions close to what is recommended. So here we have a clearly elevated CO2 effect. But it also means one has to be careful to assume if light is really the limiting factor, law of the minimum you can consider, then additional CO2 may not always help. Another example is here with reddish. Once again, the daily light integral recommended 12 to 15. Here we had 12 in the highest variant, but you see there is no significant effect visible with respect to tuber yield when additional CO2 was added. Just a short note, the experiment with the reddish tuber and with the basil was performed at the same time in the same glasshouse, so we can exclude that something went wrong with the CO2 enrichment. This experiment is especially interesting because it is different to the Phytobox results in Berlin, despite the fact that the same reddish cultivar was used in both experiments. So we have to be quite careful with interpreting the experiments and taking everything for granted, because for whatever reason, in different localities, you can actually achieve different results. Well, as I have mentioned before, the general overview of the results performed will be presented later, so I decided to give you some more information about the yield quality. Here at the example of basil leaves, and we had 4 repetitions here and looked what is the result of shading. The important changes are marked in red, also in the next slides, and you can see in basil in all 4 experiments the carotenoid content of the leaf was significantly increased. Carotenoids, they also contribute in the leaf to light harvesting, and this may explain why we have here a higher amount of carotenoids in the leaf as the plants tried to optimize the harvesting of light, of the lower light level available to them. In 2 of 4 experiments, we observed a reduced vitamin C content, so this may indicate some kind of lower yield quality. With respect to organic acids, it's a plus-minus result. So just to summarize, we can say there is not really a big change in leaf quality if we reduce the light level. Don't forget that is only the quality of the leaf, that is not the amount of basil that is produced. That is less under shading. Another example is our pepper fruit. How do they respond to shading? We observed in 2 of 4 cases an increase in chlorophyll content. By the way, I should say Bendigo and California Wonder are bell pepper, and cayenne is chili pepper. So in 2 of 3 bell pepper, we saw an increase in chlorophyll content. That is a very important aspect, because you all know when you buy your bell pepper, we have ripened forms, they are red. sometimes yellow, but in our cultivars basically red. And then when they are green, they are not ripened. So if we have here a higher chlorophyll content, that basically means that we have a larger amount of fruits that are not fully ripened. What else do we see? In 3 or 4 cases, we recognize a reduction in flavonoid content. Flavonoids, they serve as a UV protection, and of course it makes sense if the synthesis of these compounds is affected by light, so a reduction is not necessarily surprising. And in all 4 experiments, we also recognized a reduction of the antioxidative capacity. This is a parameter that is generally used to describe the fruit quality, some overall character. So what we can say is, yes, shading here reduced to a certain content fruit quality. On the other hand, the changes in organic acids and in the carbohydrate content were not that distinct. And you all know that the sugar-acid ratio is quite important for the taste. So the taste for the consumer, it was not affected that much. Last not least, the effect of shading on radish. I can make it short. There is only a minor effect, basically no difference. So no quality change if the radish is grown under somewhat lower light level. What is the effect of elevated CO2? I have here combined the results of the 2 basil and 2 radish experiments. In general, we can say there are not so much differences with respect to antioxidative capacity. You see in basil a plus, in radish a minus, so even opposite results. And the effect on the organic acids is also not that important. Here again, we can say for basil and radish at least that increasing the CO2 concentration did not have a significant effect on the quality of our commodities. Which brings us to the discussion and conclusion. So I would like to start with the first point. Then in hot climate, opening the greenhouse may result in a cooling trend due to the PV panels. However, CO2 enrichment is not possible. That sounds not very important, but I think that is something indeed of practical relevance, that you can have here a cooling effect with the PV modules as well. CO2 enrichment seems not to work cost efficiently when light is limiting. So this is what we have to keep in mind when we consider adding CO2 enrichment into our experiments. In practice, the application of CO2 can be recommended in a closed, controlled environment greenhouse comparable to the Phytobox of Berlin, where you do not have CO2 leakage. That is, of course, environmentally better because you are not releasing CO2 into the air, but it also means that you have to have a greenhouse that is quite expensive, say it that way. What we have not discussed here about is the CO2 enrichment improves water use efficiency. That may be quite an important point. But from a practical point of view, I would personally recommend that you should first focus on applying the optimal light level and, of course, temperature regimes and humidity regimes, because that, first of all, produces your yield. And when that is achieved, you can consider about adding CO2 for further improving yield and especially for improving water use efficiency. As I have mentioned, produce quality seems less affected by shading and elevated CO2 concentrations, yet such kind of conclusion may be cultivar specific. And a quite important point, if you are dealing, for instance, with fruits, like in our example of pepper, the ripening may be delayed when light becomes limiting. And that is indeed of practical significance, because it means either you decide harvesting not fully ripened fruits, that is green bell pepper, or you decide extending the cultivation period. But that means in practice that you consume more water to get the same yield. And even more, this could potentially reduce the number of crops and the number of harvests per year available. So here you have to do a quite tough calculation in order to optimize your farm. That's so far all from our side. I would like to thank you very much. And of course, I would like to thank all the members of the Regace team who enabled this research, constructed everything here at Boku, and as a whole made this research possible. Thank you very much for your excellent and fruitful cooperation.
Thank you very much, Norbert. I can see that there's starting to be some activity in the chat, some questions and discussions going back and forth. So please feel free to jump in there and see if you want to contribute to anything. We'll go ahead and move on now to the more digital and data-driven part of our presentations. We're going to have a little bit about the modeling and the digital twins from Cristina Cornaro from the University of Rome, Tor Vergata. So Cristina, would you like to share?
Yes, thank you very much, Raymond. And thank you to all the partners and all the people that joined the this conference, the final conference. Now, I think you can see something, but I'm going to put in the presentation mode. Let's see if it's working. Okay, can you see?
Yes, very good. Thank you.
Great. So I'm going to change my pointer just to see if you want to point something. Now let's go to the modeling and digital twin. This is the activity that we led in the project and we carried on in this 3 years period of the Regace project. As you could see from the previous presentation, the PB greenhouse ecosystem is a quite complex framework in which 3 interconnected systems interact within each other that are microclimate, crop, and photovoltaics. As you can see from the picture, the PV system is going to intercept the solar radiation coming from the outside, shading the crops. On the other side is also providing heat to the greenhouse, modifying the microclimate. Moreover, the microclimate, as we all know, is driven by the external weather condition, but also modified by the crop inside the greenhouse due to evapotranspiration. And the crop, due to shade, are influenced in their growth and also in the water uptake. Overall, obviously, the microclimate is influencing also the crop growth. So with such a complex interaction and complicated system, also the modeling is quite challenging. We can so build a predictive model in different ways. in order to enable evaluation of design choice and also control strategies. We could approach this problem in a physics-based way, in which mathematical equations are used to describe the physical processes inside the system, providing the request output, or we can use machine learning or stochastic models that need to learn about these processes from the data input, a large amount of input and output data that needs to be used by the neural network in order to be trained and tested. In our Regace project, we use a physics-based and machine learning integrated framework, trying to use a physics-based model to better understand the behavior of the three systems, microclimate, crop, and PV, and using at the end a machine learning framework in a way that all these processes could be combined together in order to give a more operational digital twin useful for control, mainly for optimization and control strategies. So I will start to talk separately about the three different framework, just making an overview of what we have done during these 3 years. It's a large amount of work, so in this case I will not show directly our more scientific results, but if somebody wants to go into deep into this consideration, I have extra slides and I can show you later on. Let's start with the microclimate modeling. For this purpose, we used a well-established dynamic building simulation software tool called IDA-ICE from Equa Simulation. And we adapted this tool in order to model the internal microclimate of a greenhouse. To do this, we had to make some modification to the original model, customize the thermal zone, that is the environment where the heat balance is calculated and provided, introducing the evapotranspiration of the plants in order to take into consideration the variation of microclimate induced by the plants. So the other important thing that we could add in order to simulate dynamically the growth of the plant was the introduction of tables with leaf area index and the plant conductance variation with time, in order to take into account for the plant growth during the period of simulation. So introducing the location, custom weather file, geometry and orientation of the greenhouse, and the thermal and optical properties of the envelope, we could make two models, one for the FSC greenhouse that you see over here in Italy, and the other one for the UTH greenhouse pilot in Greece. We could validate the model with the experimental data, and we obtained very, very accurate results. Now I can go on to another kind of modeling, a stationary kind of modeling, that is computational fluid dynamic, that has been applied in order to understand the 2D distribution, 2D and 3D distribution of the environmental variable in a certain time. And here the model has been built in the ANSYS Fluent environment for the UTH greenhouse pilot in Greece. And two interesting features has been evaluated. The first one regards the higher irradiance levels in the upper part of the greenhouse, as you can see from the top heat map. The red part of the top represents high values of irradiance, and this is probably due to multiple internal reflection, and this was also confirmed by some experimental measurements. The other feature is was already observed in previous presentations, is the heat accumulation due to the PV modules that is confined, as you can see, in the upper part of the greenhouse, not affecting the lower part where there are the crops. Going to the crop modeling, we also in this case use the physics model, the well-established FAO aqua crop model that can simulate the crop yield and irrigation demand for a wide variety of crops. And we applied this to the greenhouse in Italy, the FC greenhouse. The plant of the greenhouse is here represented, in which you can see that we had 4 sectors. The west PV, east PV, west no PV, east no PV. And the west, this side, were planted with the different crops, in particular for this case, tomato on the east and eggplants on the west. And we could use for the FAO aqua crop model the no PV part of the experiment in order to calibrate the model. Providing all the input data that you can see over here in the sketch. Then we could validate the results of the crop yield on the other section, the PV section. And what we could observe is that in this case we could catch the lowering of the production due to the shade that, as Norbert said, is something that can happen in our greenhouse. Going to the PV performance modeling, we just use 2 models in parallel. The PVlib model that is provided in the PVlib library, what is a well-established model, and we also built a data-driven physics model called the DBPC2 model, using the experimental data coming from the UTH pilot in Greece and the other FC pilot in Italy. What we could observe is, first of all, what we wanted to do is having the PVlib as a benchmark to try to understand something about the real performance of the PV system. What we could observe is that is represented in this graph for the FSC. Sorry, I have to drink something. For the FSC pilot, in which in green you can see the performance of the PV system provided by the reference, the benchmark, so the PVlib. In red, the observations, and in yellow, our DBPC2 model. As you can observe, there is a wide difference between the benchmark and the observation. And so this was investigated, obviously, in order to understand what was the problem that could affect the performance. And we found out that, as already mentioned by Ibrahim, the internal structure of the greenhouse is going to shade the PV system, lowering the performance. On the other side, we just tested our model, the BPG model, that is driven by experimental data. So in this case, it's going to catch also the shading effect in the real world. And in this case, we could model the performance of the system in a very good way, reproducing very accurately the performance observed. So this model could be useful for maintenance and control strategies in the greenhouse. Now let's go to the digital twin. During this 3 years, we just applied to our data different kind of machine learning technique, starting from recurrent neural network, going to the state-of-the-art graph neural network, and finally we went to the XGBoost machine learning framework that produced the better results. Moreover, in our test, we just decided to lower the amount of variables to be injected into the model in order to speed up the computation and building a so-called low-cost model, being able to use this in the real world, so in an operational setting. Here I'm going to show you two different workflows about the digital team that we built with the XGBoost low cost, one that considers the prediction of the microclimate only, and the other one that can predict in parallel microclimate and photovoltaics. We started from the input of external weather condition at a minutely rate into the XGBoost algorithm that could provide the most important internal variables for the greenhouse microclimate that you can see here represented. You could, I think, understand which kind of variables they are. Then we could elaborate these variable in order to provide daily values useful to feed the aquacrop model in order to produce the daily crop yield. As you can see in this structure, the internal microclimate is predicted by a machine learning algorithm, while at the moment the crop yield is predicted using a physics-based model. That's because we didn't have very nice results regarding the crop yield evaluation using a machine learning technique. Looking at the other model, microclimate plus PV, we have always external weather in the output, but in this case, we are going to add also data coming from PV sensors that could provide information about the temperature of the modules, inclination, orientation of the panels, and irradiance on the front and on the back. We injected this data into the XGBoost low-cost algorithm, and that could provide the internal microclimate variables and the PV production at a minutely rate. Then we go on with the daily values of internal microclimate to inject it in the aquacrop, and so in parallel we could provide daily crop yield and PV yield from this analysis. Going to the conclusion, what we can see is that we developed and validated a predictive simulation framework in which we combined physics-based models and data-driven approach for this complex environment. We could capture the systematic interaction between the microclimate, the crop processes, and the PV production in the real operating conditions. But future work is necessary, and that's the reason why also we want to continue with these activities, because it's important to have continuous crop sensing to improve dynamic crop modeling, improve data standardization and sensor scalability across sites, and also we need to validate the models across different climates, greenhouse typologies, and crop species. Before concluding, I'd like to thank all the team of my lab, Esther Lab, that contributed for all the model developing over here. And also I'd like to thank all the partners that contributed on this hard task during the Regace project. Thank you to all. And if there are questions, I'm here. And if you want to see something more on validation, I will be happy to show you. Thank you again.
Great. Thank you very much, Cristina, and to you and your whole team. And again, everyone, if you'd like to get in contact with Cristina, just jump into the chat, ask any questions you have there about modeling in digital twins. And now we'll move on to the broader impacts around the whole. You've seen now experimental results, and now let's look a little bit more broadly. What have been the impacts here? And we'll start with the perspectives from the farmers. We've had some work done with lots of farmers and greenhouse owners and getting their perceptions. So the next segment is from Maria Cristina Antonucci and Andrea Volterrani. They're also from the University of Rome, Tor Vergata, but from another department there. So Andrea, would you like to get started?
Yes, thank you, Raymond. Welcome to all the participants to this final conference. I give the floor to Maria Cristina. I say only for the first introduction that we have, and we present an approach about the farmer's perspective and underline these words, and I explain, and we explain after this participation of the farmers about this idea of innovation of agrivoltaics in greenhouses that you heard by my colleagues before. So I give the floor to Maria Cristina Antonucci.
Thank you, Andrea.
Start.
Thank you. I will be starting by introducing the most theoretical and methodological part of the activity carried out by Andrea Volterrani and his team. And we will start with the general approach, which is citizen science, which is a very common approach in social sciences. And it's an increasing approach within the activity of green energies and innovation in farming. So we started by introducing the general approach of citizen science and explaining which are the main reasons that drove our activities. Especially, we detected the growing relevance of citizen science in the area of sustainability. We understood that this kind of approach aligned well with the global activity of giving even more participation, giving even more voice to the end user of innovation and technologies. And this kind of approach also helps us introducing the more democratic activity and the shift from top-down science, in which researchers and scientists develop new technology and innovation models, and transfer this new technology to the end user. In this kind of approach, the activity of production of science and technology is co-produced by end users and scientists. So also end user can help scientists and researchers with practical observation, practical perspectives in the development of innovation and science. This also helps our activity of having farmers participating and not only responding to requests on data on their use of technologies, but also helps farmers become active subjects in the development and translation of scientific innovation. And this helps also with the getting local expertise in the 5 contexts of the Regace projects, helped receiving context-sensitive evidence from the different contexts where the greenhouses were installed, and also added some an experiential touch from their part. So while considering this general perspective, we delved into the farmers' participation and add farmers, especially during the third part of our activity, the participatory word cafes, having farmers being exposed to the innovation and the technology. So this helped a lot testing the technology in real world condition. As you can see, we have a picture taken from one of the word cafes we held in Greece. Helps enhancing data quality through the experiential grounding, and also incorporates the perspective of farmers in the research process. So what we did during this period of time, of the 3 years time, during the activity of the social and participatory work package, we try to detect the perception of farmers on APV with 3 types of method: quantitative, qualitative, and participatory. We decided that the best way to get a real perception of farmers' face to the innovation that the APV Regace project proposed was to collect different kind of types of methods. So we started with the quantitative method to get the general perception of farmers with the questionnaire, in order to get the relevance of this new of this innovation, of the APV innovation, and this helped us identifying the general patterns, the general needs, and the adoption potential across the countries. This questionnaire was distributed into the 5 countries which are partners of the Regace project. Then we decided to get more in deep with the qualitative methodology, and we had some interviews, 48 in-depth interviews with some farmers, posing more in-depth question about their perception of APV and the possibility of adopting APV in their own farming activity. Then we used participatory methods in Work Cafe in order to evaluate the potential impact of APV, of the innovative model of APV proposed by the Regace project, in order to have people discuss the potential and their pros and cons of the model after being exposed to the Regace project model. And this kind of definition of methodology took us to 3 different research phases. We started with the research training and networking, which was held throughout a spring school, where scholars with different kind of background, scientific background, came to Italy and held a spring school where they learned some of the most relevant methodology for social and participatory sciences. So this helped us go through the next phase of research, the empirical data collection, where the questionnaires, the sentiment analysis, the in-depth interview, and the work affairs were conducted by Andrea's team and also by the attendees of the spring school who helped us through the process in Greece, Austria, Germany, and also in Italy. So this activity of empirical data collection helped us to better map the perception of expectations of the involved participants to this questionnaire, sentiment analysis, in-depth interviews, and work affairs. And so that we arrived to the final phase of our activity, of research activity, through the data analysis and the reporting, which integrated all the materials from the qualitative, quantitative, and participatory analysis, and helped us develop a complete, socially robust assessment of the APV perception among the involved farmers. So this is the most important activity that we conducted during our 3-year period of research of social and participatory research in Regace. And I now leave the floor to Andrea, which will explain which are the main results in his analysis of the conducted activities on the 148 questionnaire, 146 sentiment analysis, the 44 in-depth interviews, and the 8 work cafes. Thank you, Andrea. The floor is yours.
Yes, next slide. Thank you, Cristina. And very quickly, I try to explain the main outcomes and insights because the methodology it's a very well-known approach that is the citizen science, like Cristina says before. And so we have 4 main outcomes. The first of all is the knowledge co-design across stakeholders, communities of farmers, because the dialogue between scientific and experiential knowledge it's very crucial to create the condition to have an innovation that are accepted before the conclusion, the prototypes. The second is the complementarity of research methods that we have used, qualitative and participatory approach. The third main outcomes is the interdisciplinary and cross-sector exchange, because obviously when you have the opportunity to hear the different point of view, different position about the innovation, the technological innovation, it's enrich all the things around the innovation. And finally, the value of participatory formats, because in this case, we have the opportunity to hear the real voice, in this case, of the farmers. The next slide. On the questionnaire, there are 4 also in this case main outcomes. First of all, the awareness of benefits is widespread, while familiarity with APV it's very various between the farmers. Sometimes it's a good way to accept this technology. In other case, they have many different ideas about agrivoltaics and the use of agrivoltaics. There is a second cautious openness to adoption because it depends on incentives, on the regulation, and obviously on the technological stability of agrivoltaics. The third question that emerged by questionnaire is the economic and institutional factors that as key drivers to support costs for the energy prices about the energy production by agrivoltaics, and eventually policy incentives that institution can adopt or not about agrivoltaics. And finally, the perception on APV shaped by uncertainty and information gaps, because sometimes the farmers have needs to more information and more clear information about the technological innovation. Next slide. For the deep interviews that we have made, other questions feasibility on the economics cost, and the agrivoltaics must fit with current farming practices. It's not possible to put an innovation in the everyday life of a farmer. The second point is that emerged from interview is the central role of experiential knowledge. Farmers put in evidence their knowledge that derive from the experience on the field, and in this case, it's very interesting. The third question that emerged is the APV perceived as a socio-technical trade-off, and in this case, benefits are balanced against productivity, regulatory landscape, and governance risk. And finally, trust and participation has enabled the condition, and so the transparency, the fair benefit sharing, and an important point that we will see on the next slide, the early engagement of the farmers in the acceptance of the new system of agrivoltaics. The next slide. Work cafe. The work cafe is the main methods that we use to create and to facilitate the participation of the farmers. And so the main results of the work cafe, you see some photo in different places where we have the opportunity to make these types of methods of participation. In this case, the first outcomes that is a collective identification of conditions required for APV acceptance, and so they identify in each work cafe that requires economic, regulatory, and technical stability. The second question is the necessity to create a co-constructed framing to create the condition to expand agrivoltaics in the local community. The third question that emerged, the priorities about the perception by the farmers in these methods are the fair benefits, the productivity protection, and the long-term reliability of the APV innovation. And finally, the work cafe supported learning, reduced uncertainty, and shaped feasible APV pathways among participants, because they see and they have experience about in each place about the experimentation of the photovoltaics in the greenhouse. The next slide. Okay. And so the farmers' participation key takeaways, farmers' participation strengthens relevance and impact, because Participation and co-design grounded analysis in real production conditions and enhanced legitimacy, trust, and usability. And mixed methods enable robust analysis of social technical innovation because the integration create the condition to understand better the PV adoption. And finally, the citizen science enhances knowledge quality, in this case, in farming and in society. Next and final slide. So what are the lessons learned and the future perspectives from the activities of farmers' participation? The first of all is to create the condition to start from co-produced knowledge with the participatory and the citizen approach to go to the policy and practice, obviously, because it's important to use these results to change and to support the action to change something. The second is to strengthen long-term researchers' stakeholder collaboration. It's not only punctual on a single innovation, but the collaboration between researcher and, in this case, farmers became stable. And finally, about the future perspective, it's possible to apply the participatory co-design in new context without. It's important to apply this without compromising rigor or local relevance, to have an approach that is possible to use in different contexts. Thank you very much. I say only thanks not only to Maria Cristina Antonucci, but all the staff that participate on these types of approach. And so Stella Iezzi, this is another professor from Tor Vergata, and Fabiana Battisti, and Marco Serra, that obviously nowadays that are not here. Thank you very much.
Good. Thank you very much, Cristina and Andrea. And yeah, let's just keep it moving from farmers' perceptions to the overall impact and sustainability aspects. This will be from Liron Amdur. She's from Tel Aviv University in Israel. Liron, would you like to share?
Yes, can you see my presentation?
Yes, very good.
Very good. Okay.
Thank you.
So,
Go ahead,
thank you.
please.
Yes, as I said, when I go to the next slide, you see the next slide? Everything is fine?
Yes, background
Okay.
slide. Yeah.
Yes. Okay, so I will talk about the overall impact and sustainability. And the first question is whether really greenhouses, which is what Regace project focuses on, can in any way contribute in a substantial way to achieving the EU renewable energy goals. As we know, the EU set about 3 years ago a binding target of at least 42.5% renewable energy for 2030. It's 4 years from now. And as we probably know, on the other hand, the greenhouse sector in agriculture is rather small. So the question is, first of all, is can it really make a difference to put all these solar panels into greenhouses? So the first analysis for me was to look at all the goals, all the renewable energy goals of all the countries in the EU, 27 countries, and to look at the area of greenhouses in these countries. And of course, taking into account the energy production that is possible with our technique, to look at how much land would you need for greenhouses to have in order to cover all these renewable energy goals, and what is the actual size of the greenhouse sector in each country, and then to look at how much of these renewable energy goals can be covered by integrating solar energy into greenhouses. So we see that in some countries, such as Israel, for example, the greenhouse sector is a little bit bigger than in other countries, and the solar panels can cover up to 45% of all the renewable energy goals. In other countries, in Germany, in Austria, where the greenhouse sector is smaller and the renewable energy goals are bigger, then it can only cover about 2 or 3.5% of the renewable energy goals. But overall, in all these 27 European countries that I studied, on average, 23% of the renewable energy goals can be covered by placing solar panels into greenhouses. So this is pretty substantial. So yes, this could really contribute a lot to achieving these environmental goals. And then when we look at the sustainability aspects, of course, we have to compare our technology in the greenhouses to other things. So the first comparison is with agri-PVs in open fields. That is on top of plantations, in field crops, for example. We know that there are these kind of technologies. When we suggest to put the panels inside greenhouses, are we achieving any sustainability benefits? So I looked into the economics. Of course, we know sustainability is made of 3 pillars: social, environmental, economic. So on the economic part, I looked into the upfront investments. Are the investments for putting the solar panels inside greenhouses larger or smaller than to put them in the open fields? Ease of installation, of obtaining permits. We know that in some cases it's harder, in some cases it's easier. When we talk about the social, what are we benefiting small family farms more in the greenhouses or in the open fields, rural development in general? When we talk about environmental issues, what are we contributing to the conservation of natural resources, water and other materials? Of course, CO2 footprint, water footprint. This I will show the results in a minute. And then we also compared the agri-PV greenhouse versus a greenhouse without PV. Some of the other presenters before me already mentioned some of the results, but I will show the overall results of all the teams that worked together in crop yields, in irrigation efficiencies. We also tested in Israel the issue of arthropods. It was a very special test. Do we see more pests or beneficials, insects in the greenhouses with the PVs or without them? And of course, there is the additional income from the electricity production. So first of all, I will talk about the comparison of the greenhouses, the solar greenhouses to agrivoltaics on open fields. I studied it using a very, very large literature search of all the publications that I could find that relate to the economies of agri-PV in open fields. Then I studied all the projects that already exist in Israel. That's about 6 projects in open fields and 24 projects in greenhouses. And of course, I compared everything to the results of our installation with the Regace project. So first of all, the results about the economic, the upfront investment. We see that in our project, when we place the panels inside greenhouses, the cost of investment is 24% lower than what we see in open field agrivoltaics. And this comes from 2 important parameters. One is the structure for mounting the modules. In greenhouses, we don't need to build a new structure. What we need to do in open fields. In open fields, we have to build these very, very big structures, these steel and iron structures to hang the panels on top or over the crops. In greenhouses, we just place them on the greenhouse itself. So it's a lot cheaper. And because we use already an existing structure, the installation, the labor in installation is much, much lower once you put the panels inside greenhouses. So this is, again, another element that saves on the upfront investment. This is, of course, very important, one, for the farmer, and the energy companies, but also to roll out more and more renewable energy into actual existence, into implementation. When it's too expensive, then not so many people implement this technology. When it comes to CO2 footprint, as I said, when we go to the open fields, we need to build very large mountain structures to put the solar panels on top of them. All this iron and steel that we need to use for these mountain structures, they use a lot of energy to produce. So once you calculate how much more iron you need to build these structures in open field, you see it's more than 2 times as much as we needed in order to place these panels inside greenhouses. This translates into a CO2 footprint. So on one hand, we try to lower the CO2 footprint by going into renewable energies, but then we waste it on building a lot of iron and steel structures to hang the panels on top of it. So once you place them inside greenhouses and you use the structure of the greenhouses, you save on all of this energy and pollution. And the same goes for water footprint, because producing iron and steel also consumes a lot of water. Once the actual water that is used inside the production, and also a lot of water is being polluted by the production process. Once you use a lot less iron, you save also on this, and you can see here the difference. Now I go into the comparison of the agrivoltaic greenhouses to greenhouses without PV. So first of all, an overview of the experiments that we did. We had 24 trials altogether, crop trials in 6 different sites that are located in 5 different countries. We had 2 sites in Germany, but otherwise in Austria, Italy, Greece, and Israel. And we tried 8 different crops, many experiments with cucumbers, but also with lettuce and tomato and bell peppers and so forth, as you can see here. And we also did the trials in different seasons, because this is also important on the impact of the panels is the season in which you grow the crops. I will show you the results soon, but most of the trials were conducted during spring and very few in the autumn and also in winter and summer. So what do we see overall in all of the results, 24 trials, is that PV indeed lowers the yields in the greenhouses that were with PVs. The yields were about almost 27% lower than in the greenhouses without the PV, with the same crop and the same season and the same agricultural interface. But it was a little bit better in the Mediterranean countries, that is Israel, Greece, Italy. The difference in yield was less than 12%. So there is an impact, but it's a lot lower in the Mediterranean climate countries, and in the more northern European countries, it was higher. Another thing that we observed were the effect of the type of crop and the effect of the season. So we distinguish between 3 groups of crops: fruity crops, that is like cucumbers, tomatoes, bell peppers, where the crop is the fruit of the plant, and leafy crops, lettuce, basilicum, where what you sell is basically the leaves of the plant, and then tubers, like radish. And we see that the biggest difference between the greenhouses with PV and greenhouses without PV is in the fruity crops. That's about 400 grams per plant. Whereas with leafy crops, the difference was much lower. And also for the season also plays a very important role here. You see that the difference is the highest in summer. It's more than 350 grams per plant of difference between the greenhouses with PV and greenhouses without PV. Whereas in winter, it's almost the same. There is hardly any difference between the greenhouses with PVs and greenhouses without PVs. Irrigation. Of course, we can measure the amount of water that is being used and then compare it between the two greenhouses, but it makes more sense to compare the irrigation efficiency, that is how much water is being used per kilogram of produce. And we see that there is a problem. We need to use a lot more water in the greenhouses with PVs than in the greenhouses without PVs, but probably it has to do with the fact that the yield in some of the greenhouses with PVs was lower. So this is why we had to use a lot more water in order to reach the same yield. I must say, again, in the Mediterranean countries, the difference was much, much lower. It was about 2%, 3%, not the 48% like we see here. So there the experiments were going a lot better. When it comes to insects, pests and beneficials, the picture is really, really mixed. On one hand, we see a significant increase in the number of mites in the greenhouses with PVs. We don't see any consistent effects regarding thrips. We see even reduction of tobacco moth aphids in the greenhouses with PVs, so it helped a little bit. And when it comes to beneficials, again, the effect is inconsistent. So here we are really not sure what we can say, which kind of greenhouse is better for agriculture with PV or without. So I'm reaching my conclusions. First of all, yes, PV panels, integrating them into greenhouses can substantially contribute to the achievement of the EU renewable energy goals. So this is something to promote. And in many ways, it is really preferable in many sustainability aspects to agrivoltaic system in open fields. Okay, we have lower investment costs, as I said. It helps better small family farms than larger agricultural corporates. It's the CO and water footprint is much, much lower. So there are many benefits. However, it doesn't have an impact on crop yields, especially in more northern countries. In Mediterranean countries, like I said, the difference is very small. And if we want to even reduce this impact, we can adapt some types of interfaces. For example, combining the PV with greenhouses where leafy crops are grown, lettuce, basilicum, this kind of things. Or in the winter crops that actually it sort of go together, because usually lettuce is a winter crop. Then we will see a much smaller differences. And prepare for treatment of mites, because this is probably something that you will see in areas where there is more shade, and this kind of pests prefer this kind of environments. So that was my presentation. I would just like to thank all the team of the Open Landscape Institute and the Entomology Laboratory of Applied Ecology and Professor Tamar Dayan from the Museum of Natural History of the Tel Aviv University that all helped me with this study. Of course, all the team of Regace and all of you for listening. Thank you.
Thank you very much, Liron. Very interesting. I know that Liron has to leave in just a few minutes, so if you have any questions...
No, I can stay actually, very much.
Okay. You changed of schedule. That's great. So, but still, if you have questions for her, jump into the chat and let her know, and you can have follow-up questions there. And we will continue moving on now from overall sustainability into policy and talk a little bit about the policy recommendations for agrivoltaics, legal pathways and regulations that are important there. And that will be from Ezgi Ercan. She's from Timelex law firm in Belgium. So Ezgi, please take the floor. I see your slides already.
Thanks, Raymond. It's full screen, right? The slides.
It is. Perfect.
That's perfect. Hi, everyone. My name is Ezgi Ercan. It's a pleasure to be here. Thanks to our organizers and thanks to the participants for being here with us today. As Raymond has mentioned, I'm a lawyer at Timelex. We're based in Brussels. And today I will briefly present our key legal findings from the Regace project. This talk, in fact, is based on our deliverable recommendations for improved regulations, which explores how law and policy can better support agrivoltaics in Europe. This deliverable is available online. I will share the link to the blog post we've drafted, which also includes the link to the 74-page report, as well as the recording of a webinar we have organized together with some consortium members back in June. Our time is limited today, but you can always consult these resources for more detailed information afterwards on legal pathways for agri-PV in Europe. But still today, I will do my best to give a nice overview of what our report found. So let's start by the question why legal pathways matter for agri-PV. Why does regulation matter so much for agrivoltaics? Agri-PV combines farming and renewable energy production on the same land. And while the technology is very promising, deployment at large scale requires clear and supportive regulations. This is very important for scaling these technologies in different jurisdictions. And our deliverable analyzes this legal context, focusing on the law at the EU level, as well as the 6 countries where we had the installations, including Austria, Germany, Greece, France, Italy, as well as Israel. So we had a focus of 6 national legal systems, and we've tried to do a little bit of benchmarking how these regulations work, how they can be optimized to allow the scaling of these technologies. And the main question that we started with is whether or not the EU has the competence to regulate agri-PV. This is a key policy question. And under the European Union treaties, renewable energy and agriculture are both shared competences, which means that both the European Union and member states can legislate. For renewable energy, the EU uses this competence broadly. However, for agriculture, the EU needs to act mainly through the CAP, the Common Agricultural Policy. So this division defines the legal room for new agri-PV rules at the EU level for harmonized standards. And it matters because this is the key point for either legal fragmentation or harmonization. And well, moving to today's agenda of what I would like to cover in this framework is here on this slide. So let me briefly walk you through today's agenda, which also reflects the structure of our legal study and the key insights that I will cover today. First, we will have a brief look into EU policy frameworks that support the development of agri-PV. Second, we're going to examine specific EU legal instruments that have a direct regulatory impact on agri-PV projects. Thirdly, I'm going to touch on other relevant EU instruments that while not directly regulating agri-PV, still influence important aspects such as supply chain, resilience, data management, and cybersecurity for smart systems. Fourth, I will present our key findings from selected national frameworks. And finally, we'll conclude with the policy recommendations. These are practical steps for the EU and national policymakers to remove barriers, create incentives, and build a trust in agri-PV as a sustainable solution for agriculture and energy. So that's what we will be covering today. In the first part of our study, we examine how broad EU policy frameworks provide an enabling environment for agrivoltaics. First, we have the famous European Green Deal, which serves as the overarching policy umbrella, putting the EU on the path to climate neutrality by 2050. This encourages innovative renewable energy solutions to meet these, let's say, ambitious emission targets. Secondly, the EU solar strategy is highly relevant because it recognizes integrating solar energy into agriculture as a strategic priority for boosting Europe's energy security and decarbonization goals. This, in fact, is a direct policy endorsement for agrivoltaics as a practical solution for expanding solar capacity without competing for scarce land resources. Third, the Common Agricultural Policy, the CAP, it plays a very central role. It does not only provide direct payments to farmers, but also it supports a sustainable rural development. The dual use of these technologies, in fact, must be seen as an innovation that aligns with CAP's sustainability goals, rather than as an activity that could disqualify farmland from support. This is actually why CAP matters so much for this topic that we researched from a legal standpoint. And lastly, the regulation on the governance of the Energy Union and climate action. This obliges each member state to prepare national energy and climate plans. I'm really sorry, but there is a participant that needs to mute their microphone. If that can be taken care of, that would be great. But at any rate, together, these frameworks set a consistent and supportive context and make it clear that agrivoltaics fits within the European Union's broader agricultural, energy, and climate ambitions. Moving on to my next slide, beyond these very broad legal frameworks, there are also more specific legal instruments that are of direct relevance to these technologies. A key example is the revised Renewable Energy Directive, also known as RED III. This directive, which is now being transposed into national law, and some member states have taken some steps, mandates faster permitting times for renewable energy installations, which includes agrivoltaic systems as well, hence the relevance. This is critical because lengthy and complex permitting has historically been a major barrier to deployment of these technologies. And these rules are obliging member states to simplify and expedite these processes, Initiatives such as this one can significantly accelerate new projects that are being deployed. And closely related to this is the regulation on the accelerated deployment of renewable energy, which actually explicitly recognizes that renewable energy projects such as agrivoltaics as being in the public interest. And such legal status reduces the burden of proof for demonstrating the necessity and benefits of deploying such technologies. And this simplifies planning permissions and reduces the legal hurdles that often either delay or block such projects. Moving on to my next slide, this will be the final general slide that I have on laws at the EU level, is supply chain data and cybersecurity aspects. Timelex is in fact a law firm that is active in the cyber domain. We do mainly technology law, so this is also very interesting in this regard. And the EU is actively shaping the broader digital environment in which agrivoltaic systems are manufactured, deployed, and operated through legislation targeting either supply chains, data access, and cybersecurity. First, instruments such as the Corporate Sustainability Due Diligence Directive and the Critical Raw Materials Act push for more sustainable and also resilient supply chains. For agrivoltaics, this means that sourcing photovoltaic panels and components must comply with stricter environmental and fundamental rights standards. It also encourages more local production in the EU to reduce reliance on imports, which can improve supply security but may actually raise short-term costs. Next, the Data Act, which is actually the first point on my slide, has direct implications for advanced agrivoltaic systems, especially those installed in greenhouses, the smart systems. These systems really generate large amounts of data on energy production, crop performance, environmental conditions, you name it. The previous speakers have already pointed towards the value of such data. And the Data Act empowers the users, such as farmers, to access and control this data, improving decision making and also the efficiency of these systems. The Data Act also requires robust data sharing infrastructure and clear governance rules to handle data ownership, as well as privacy and data protection in a responsible way. Maybe I can talk about next on cybersecurity. On the cybersecurity side, we have the NIS2 directive and the Cyber Resilience Act, which set higher standards for protecting critical infrastructure against cyber threats. And as agrivoltaic systems become more connected and digitally integrated, they also become potential targets for cyber attacks. And compliance with these laws mean that operators must invest in secure network architecture, incident response capabilities, and proper training. And in fact, while these raise operational costs, it's also very, very necessary to safeguard energy security as well as the integrity of the data that is being collected. And I also would like to speak a little bit about eco-design standards. Because eco-design standards are also incredibly relevant for photovoltaic components to ensure that these panels indeed meet defined sustainability criteria through their life cycle and further support the EU's green objective. Okay, Okay, moving to my next slide. I'll be brief because I see we are running low on time. In addition to the EU level framework, we also analyzed the national legal frameworks of 6 countries. And as the result of our research, we have seen that France and Germany have the clearest rules for agri-PV, including legal definitions and requirements for minimum yields. But even there, complex permits and limiting financing can slow deployment. And then Greece and Italy showed rapid policy developments, but faced challenges with grid capacity and fragmented laws. Austria has significant regulatory gaps and limited economic incentives, yet there is emerging recognition, which is very positive news. And overall, we have identified many national differences that highlight actually the need for EU-level coordination for scaling of these technologies in the region. And the report remains available for detailed findings on each of these countries. And moving to the policy recommendations, based on our analysis, we developed practical recommendations for EU and national policymakers. To begin with, the Common Agricultural Policy should explicitly ensure that agri-PV installations do not disqualify farmers from receiving support, and mechanisms should be established to monitor compliance with legal standards so that these incentives are used efficiently and effectively. And then simplifying and shortening permitting procedures for renewable energy projects is really crucial on the agricultural domain. Coming to the third recommendation, it is necessary to clarify that agri-PV projects are permissible on agriculturally zoned land so that this zoning does not disqualify agri-PV projects. And then states are also encouraged to implement dedicated support schemes for agrivoltaics to enhance rural energy grid infrastructures and to provide incentives for agrivoltaics also in tender evaluations. And clear tax benefits and guidance on benefit sharing across the agri-PV value chain could further incentivize adoption of these technologies by farmers. And finally, stakeholders must actively address misinformation and disinformation to build public trust and awareness around the benefits of agri-PV systems. As mentioned, the legal and policy frameworks around agrivoltaics are evolving. Actually, these are evolving very rapidly. And during the preparation of this deliverable alone, we observed numerous legal changes. And the first example of restrictive measures also in certain areas. So these policies are also highly connected with the political will. But the overall momentum is positive. The sector remains dynamic, and there are some challenges that need to be addressed. The fast-moving legal environment highlights 2 critical needs: continuous monitoring and adaptive policy making. And well, in summary, while Europe has made progress, achieving the full potential of agri-PV will require continued research funding and clear, consistent legal frameworks that evolve with this promising technology. Thanks so much. I will share the link once again on the chat so that you can consult our study if you would like to.
Thank you very much, Ezgi. As usual, regulations in the EU are difficult and complex and multiple countries and multiple levels. So thank you for shedding some light on that. Let's now move from policy to business. We definitely want to take this research from a research stage to a market stage. The technology has been proving itself, and our next presentation is about that, from research to market. From Antonio Rawad Nassar, he is from our business partner Trisolar Limited, who's the main installer of this technology and all of these greenhouses, and the organization that wants to take this to the market. Antonio, are you there? Can you share your screen?
I'm here. I'm here.
All right. Thank you.
Hi. Hi, everybody. Okay, let me share. So,
we're pushing our time here, so if you can be efficient in your presentation, thank you. And go ahead.
yeah, I have. I know that we are running out of time, but some of the colleague has been talking about some argumentation that I would want to talk about this. So I think I will be strict into talking into economics. My research and my speech is about how to take this Regace research to the market. And
can you put that in full screen mode so we can see a little bigger version?
It's clear?
There we go. Thank you so much, Antonio.
You have probably heard some of my colleagues previously talked about what is the requirement for energy that the European community is asking right now, and the based on the latest data, the renewable shares that has been achieved by 2024, it's almost 25% out of the total energy, with target to reach 42% by 2030, which is mean another 17 points. If we translate this capacity, we are talking about 440 gigawatt needed in order to cover the total requirement, let's say the total target of the European markets. The challenge, what we are finding here is Europe mostly would like to deploy in 5 years. The land use will have a big conflict between agriculture and energy, because a lot of farmers would like to understand how they can use both of them, and also the regulation, as we heard from my colleague before. So the Regace solution was to put both together in symphony, let's say like that. The top of the greenhouse become a dual use infrastructure, where in the top we have the solar energy, and in the ground we have the what's so-called agriculture. With that, we started after that all the research that came. Let's talk why before Regace having a kind of economy business within the greenhouse was a little bit difficult, which is we're related only to agriculture. We never know before the research of Regace how much and what is the yields inside each and every greenhouse. Today we know that we can produce around each 1,000 square meter around 50 kilowatt, which is quantifiable, manageable, and understand how much we can also get revenue from that. Every greenhouse before was a kind of custom engineering that need to be done. We don't know the cost. The capex were unknown before even spending money. So that was creating a bit risky for any farmer to get into this kind of business investments. The cash flow model is normally, if we are talking in terms of business, unknown, uncharted, and that makes things for bank very difficult to underwrite loans or finance any project based on that. And also, this has created a kind of a block for investor to finance any unqualified risk. Bottom line, it was a complete risk, non-calculated, that doesn't have any kind of its numbers. Now, what Regace did actually through the years, and I will go here in this slide very shortly because a lot of my colleague has been speaking about it. It confirmed all over 5 countries of Europe, which is create a kind of repeatability and proving standardization possible and proved results. The yield energy correlation, which created a kind of risk quantified. We have quantified the risk. We know how much the output from that, and we unblocked the financing situation for that. The cash flow model and has been we are able today to calculate the cash flow model in each and every project from a single 1,000 square meter to a 10 hectare even project. So this is create a kind of a possibility to go to the bank and get financing and loan approvals. Then we have also the policy that has been aligned with my colleague has been speaking about for a long time. So the Regace has created reduced the uncertainty, reducing the uncertainty, which has created a market opportunity. And here, after we have created the market opportunity, we can see how much, and we can define the European market in terms of dollars, let's say like that, if we don't want. Total area estimated from that existed in dunams in Europe, based on the data found in 2025, around 405,000 hectares of greenhouses. 405,000, which is around 117,000 units. Okay. Mostly concentrated in Spain, Italy, Netherlands, and Germany, and Greece, of course. These, if we think about the market opportunity, we are talking about market value that today exists around 11.5 billion, which is expected by 2030 to increase to 22 billion. And with CAGR depend on area between 4 to 8% during Europe. And this is another view how we would like, as a company, as Regace, to think about where we will go with the market, with agrivoltaic market in Europe, using the technology of Regace within this greenhouses. We have decided that we have studied, after studying the market, if we will go to 2.5% of market share, that will create around $2.5 billion by 2030 of business, that this long time research will come up. And this will be supported by a lot of policies, a lot of incentives that the European community is giving right now and today. So these policies and incentives that the European countries are giving, and the EU will create a kind of reducing of the capex for agriculture, which will increase appetite, let's say, or awareness to create this kind of double income. From one side is agriculture security, maintaining it, and the second side is generating new clean energy. There are some differences based on from the revenue side for each and every greenhouse. Now, we all know it depends on the sun. So the European community, the European countries, continent is completely different from north to south. And the average yearly hours per area is a little bit different. So if we go to the north, towards the Netherlands and Germany, we can get up to 1,200 hours per year of sun. If down to Central Europe, we reach around 1,300 hours per sun, and then in the Mediterranean area, we can reach about say 1,600 hours, 14 to 1,600 hours per sun. That will create a kind of, based on the incentives and based of the, I'm not gonna go into details here. I have put some kind of yearly income per 10 hectares, which means 500 kilowatt per installed. To give us an indicative, like 10 hectares in the north of Europe will give us roughly pure energy around 65,000 euro income. In Central Europe, 71, and South Europe around 83,000, which will take us to the next slide that everybody is asking from the farmer, how many years I need to invest from my money to get back my capital return of investment. So if we go into without subsidies, from south I will go from down to up. From south we have around, without any kind of subsidies and incentives from the government, we are around 6 years, 5.9 to 6.5 years in some areas. But depend, of course, on the cost, on the final cost of each project and structure. If we go a little bit up to the Central Europe, we can reach around 8.5 years. And in the North Europe, where Germany and Netherlands, we can reach 11.4 years. But with that, there are differences and incentives in Europe, and almost all Europe today adopting this incentives to bring it. So if we would like to take a clean picture, if from south we start at 3.6 to 4 maximum years return on investment, to Germany and north we reach at 7 years maximum return of investment with incentives. And this benefit not including any upside, let's say, benefit and saving of the water or anything. It's just we had made the calculation only on pure energy. And here, the EU funding mechanism for agrivoltaic that my colleague has been talking about, and I just put it in the symbol because of the lack of time. I'm not going to go here for details, but there are different tariffs. Each country has applied tariffs and benefits for each farmer. Mostly, we are talking about like the CAP strategic plan at national level of 40%, Italy PNR at 40%, EU innovation around 60%, maximum subsidiaries. It depends on the project. The project can get from a minimum to a maximum 60%, let's say like that, depends on when we present it for approval. One of the most important advantages of Regace, and my colleague has speaking about it, that we have a very important 40% almost advantage on installation, because other competitors that are sitting in the agrivoltaic sectors today, they are using scaffolding, they are using metals, they are using covering also, even the ones making above the greenhouses. So they need a huge capital to build the structure, and after that to put the solar, the OPVs on that. Regace has created a kind of plug-in, which create a cost saving, time saving, and created to be one of the most advantages in terms of price in Europe, based on the other competitors. One thing that I haven't also speak here in my presentation, which was that based on the 3-star methodology and classification of the European regulation, the 3 methods, which is one producing land conservations, landscaping, and optimization of yield, Regace has completely responded to each and every requirement or condition of the EU, which is here. Okay. Now, the last thing, and the pathway has started by 2023 with a complete 5 years, 5 countries validated. The commercial, we started to build and development, the strategy developed by 2024. We had a very first test or revenues in 2025, getting from the system and tested in Israel. Then we are planning by 2026 expansions to Europe, and of course, including consolidating Israeli market, and with targeting the 2.5% by 2030 of having market quota from European market. This is my kind of success story. From research, funding, research, so it's a kind of 5 steps that we have done. The pilot program operation matrix was validated, the knowledge transfer to commercial strategy and developed. The strategy was developed, then the market creation. We have created a total addressable market of 2.5 billion, where we can now plan it, implement it, and start the implementation. And will create farmer income stability, payback, standardized cash flow for all the farmers, and we can bring in successfully a very solid business model that was created based on Regace research into the European countries. Thank you.
Thank you very much, Antonio. Thanks for showing us that market perspective there. Yeah, with goals like that for the EU and short-term goals in 5 years, there's a lot to be done, definitely. I'm glad that some of you have stuck around this long. I'm sorry that we've pushed the time frame here. We're already over our planned time. But if you do have some questions, feel free to raise your hand. We would stick around for a few minutes if somebody does have some questions they would like to ask. We would be happy to try to answer those for you. So if anyone has a question that has not been answered in the chat already, if you'd like to raise your hand or open up your camera, you can do so. Well, everybody may be tired and hungry. Anyone? Any questions? Well, if not, then I won't push you. Thank you very much for attending from my side. Thanks to all the presenters who've presented, and of course, all of our partners who have been involved. And thank you very much for all the audience for being here. And just I'd like to hand the final word to Ibrahim as our project coordinator, just the final wrap up.
Thank you, Raymond. I would like first of all to thank all our partners for their inputs and presentation. As we conclude this conference, I would like to emphasize 2 simple, important messages. The first one is the investment in Regace really was worth it. It has delivered real value for agriculture, for energy system, and for the communities we aim to serve. The results, data, and experience gathered throughout this project clearly demonstrate the impact and potential of this project. Second, our responsibility now is to move forward with implementation on the ground. The true success of Regace, indeed, will be measured not only by reports and the presentation, but in real projects that benefit farmers, strengthen local economies, and contribute to the common goods. Now it's time to turn knowledge into action. Everyone who is interested in the implementation of Regace solution is welcome to contact us, and we are happy and ready to assist you with this. Please contact Raymond or Simon in these matters. Thank you very much for attending and wish you a wonderful day. Thank you very much.
Thank you, Ibrahim. Thank you, everyone. Have a wonderful day.
Thank you.
Thank you very
you,
much.
Jose.
And
Thank you,
also,
everyone.
Bye-bye,
all
everyone.
the best.
you.
Have
Bye.
a very
Bye.
nice day.
Bye.
Bye-bye. Raymond, can you stay maybe a few minutes?
Sure.
After that, thank you very much.
I'm stop recording now.
Yeah, very good.
Bye.
Stop
Bye.
recording.